Okay, let me check if it come okay on this side. Okay, good. All right, so good afternoon, everybody out there. So after the week break, we start again with machine learning for science seminar series. And it is my big pleasure to introduce you to the speaker for today, who is Andres Christensen from University of Basel. So Andres graduated from University of Copenhagen in nanoscience, and then he also did a PhD over there in computational chemistry. He then spent a postdoc time in University of Madison in Wisconsin, and then moved in 2016 to Basel, where he has been since, and he has been working in the last few years in essentially combining first principle methodologies with machine learning methods. So it is a big pleasure to have him here. And so we would like to kick off the seminar. The only thing, just let me give you two quick note of housekeeping. First of all, let me know if the stream has any problem through the chat box. And also, please, as usual, we will take the question at the end, just not to break the stream. But please feel free to post the question as they come to your mind, and I will go through the question at the end in the order they came to the mailbox. Okay, so without any further ado, please, Andres.
Well, thank you, Stefano, and welcome to everybody. Welcome to this talk. So I will be talking about operators in quantum machine learning and how to calculate response properties in chemical space, so essentially how to calculate properties of molecules and materials using machine learning. Yeah, so let's go to the introduction. So what are response properties? So basically, response properties are a special class of properties, and they're all quantum mechanically observables. And that means they have an associated operator, and the operator is a differential operator. So these are all energy derivatives. Here on the right side, I have a big table of some of the most known ones. And so many of them are actually something you might see in a spectroscope, like experiments from spectroscopy. For example, down here I have a picture of an IR spectrometer from 1960. And it turns out if you look in this table, you can find infrared absorption intensities as the derivative of the energy. And you can see there are some columns here. And these columns are, the first column is the electrical field, the magnetic field, the nuclear magnetic moment, and the coordinates of your molecule. And you can, for example, see here the infrared absorption intensities are the first derivative with respect to the electrical field, and the first derivative with respect to the coordinates. So basically, most things, or at least a lot of things that you can measure in experiments, can be written as some kind of energy derivative, and these are all response properties. So yeah, and also if you're a quantum chemist, most of these properties can be calculated within like the most common quantum chemistry programs. So why are we interested in this? So for example, if you want to screen chemical properties, it's good to be able to calculate these very fast. And for example, if you use molecular dynamics, one response properties is the nuclear forces, and you need those to propagate your system over time. And of course, machine learning, we hope to make that much faster than quantum mechanics. So this is sort of the background and motivation for everything that I will be talking about today. So before I really start with the talk, I want to introduce one concept that I will use a lot throughout this talk in machine learning. And this is a concept of a learning curve. And a learning curve is a pretty simple concept. So it's basically for a given machine learning model, you have a training set size. So we call that n here. So if you plot, and then also your model will have some kind of error when you try and test how good that is. And of course, if you increase the training set size, so if you increase how much training data your model has to work with, you would also expect that the error goes down. And we often plot this in a plot where we have the training set size and the error from your model here, and we call that a learning curve. And these learning curves have been shown to follow a power law. So this is due to some statistical intricacies that I will not go too deep into, but this has been shown to work both for neural networks, kernel methods, basically any type of machine learning. So the error is proportional to this, like A over N to some power. And this means that if you plot on a log-log scale, these will be linear. So essentially, if you plot the error versus the training set size on log-log scale, you will see like a linear decay like this. And due to some other statistical intricacies in data analysis and such, if you train different models on the same data, what you will get, so one model might be better than the other one, but for some reason, you will actually get these parallel learning curves. So you can actually benchmark models by looking at sort of the offset of these learning curves. So like how high they're positioned in space. So the slopes will not change. So for example, this model here, you can get a different slope, but that will require you to basically select your data differently. So for instance, through active learning or something. So I will be looking at benchmarking like models today through just comparing offsets from these parallel lines, basically on their learning curves. Okay, so let's jump into some machine learning here. So I'm not gonna spend too much time on math today, but I will give you the what I call the 1-minute introduction to kernel-rich regression. So essentially, in kernel-rich regression, you predict a property, we call it, for example, y, for a molecule, and here we represent it as some kind of vector x tilde. And you calculate that property by summing up these, so this k is called the kernel function, and you sum up this kernel function, or you calculate it, and the kernel function is basically a similarity between two of these representations. So you sum up over basically the similarity between your query molecules, so this x tilde, and then every molecule in your training set. And you multiply each of these kernels by a regression coefficients. And you can show, if you go through some hoops and loops, that this is a nonlinear transformation that will make your problem linear, and this will make it possible to also do nonlinear regression techniques. So just to show you one example of these kernel functions, just to demystify it a bit, the most commonly used, at least in my work, is the Gaussian kernel. And the Gaussian kernel is basically, so you have two representations of two, for example, molecules. And then you take the L2 norm here between them and divide by some length scale. And in the end, this will simply give you a number between 1 and 0. So you will get 0 for your kernel if the two molecules are identical, and you will get a 1 if they're identical, and you will get a 0 if they're completely different. So basically, if you go up here, you can basically see that you take your molecule x tilde, and then you compare it to all your training molecules, and you get a score between 0 and 1, and you multiply by a regression coefficient, and you add all those contributions up, and in the end, that will give you an estimate of that property y. And the good thing about, or one good thing about this is that there's actually an analytical solutions to getting a good set of alpha coefficients here. So I'm writing one solution here to this problem. You can also add regularization. That's what we use when we talk about kernel-rich regression. So you basically just have to, I'm writing in matrix form here, so you make a pairwise kernel between all your training elements. And then you multiply by a vector of all the training labels, and you get these regression coefficients in the end. But as you can see, there's like not much going into these equations. So essentially, if you want better kernel-based ML models, you have to make some better representations. So essentially, all the intricacies goes into like, what do I put into my X here? Okay, so now I will show you one of our latest representations. I will go through this representation so you roughly know how well it works, and then I will show you an example where it works really well, and then I will show you some examples where it fails horribly, and then we can talk about why it fails and how we can correct for these. So one representation that we've been developing on the past few years is called FCHL. And basically, it represents a molecule by representing its atoms. And we're doing so by using a many-body expansion distribution of the environment. So basically, I'm just writing it very generically here. So you have a collection of A1, A2, A3. So this is a one-body term, two-body term, three-body term, and so on. And basically, so for the one-body term, that just denotes what type of element we have. The two-body term, that's a radial distribution. So basically, distances, for example, from this oxygen to all the nearby atoms. And then the three-body term would be the angles to neighboring pairs of atoms here. So we place Gaussians at the radial and angular spectrum, and I'm trying to sketch it here, so I'll just like briefly try to see if I can somehow explain to you what goes on here. So if we look at this oxygen here, you can see there is a spectrum for carbon-carbon. So this spectrum here basically is a product of up to three-body terms for pairs of carbons in the neighborhood. And you can see there's a, maybe, I hope you can see it on the YouTube channel, but there's an axis here called D. So that's the radial axis, and then there's an angular theta here. And you can see there are two peaks along D here, and that's because there are two carbons at two different distances here and here. And along the theta, the angular the angular axis here, there's some other peaks here, and that's because there is one angle here, and of course this is periodic. You could like imagine having a periodic function. So we place a periodic function along that line essentially. And that way you build up all these spectra for all the different atoms involved, and you can define some kind of, so these are just mathematical constructs, and of course you can define some kind of metric or distance between these, and in our paper, we describe some involved math to do this in a sane way, which is basically solving an analytical integral. And one more thing is that these peaks here, we actually weight these terms by some empirical weight functions. So for example, the two-body terms, we weight them by r to the minus fourth term. And that's basically because we want to attribute more weight to atom configurations that are closer in space, because these are usually more important to the energy than pairs of atoms that are far away and less interacting. And the same for the three-body weight. We have this, it's actually from the three-body dispersion terms, the axolotl term here. And it also just places more weight to three-body terms that are closer in space. Okay, so I think this is a lowdown of FCHL. So let's talk about benchmarking some of these machine learning methods. So of course you need some kind of a benchmark training set and test set, and one of the most used and widely accepted sets are this QM9 benchmark set here. And the QM9 benchmark set consists of 134,000 small drug-like molecules. So I put pictures of some of them here. And they contain up to 9 heavy atoms, so quote unquote heavy. It's only carbon, oxygen, nitrogen, and fluorine. And for all these 134,000 molecules, people have calculated various properties using density functional theory, DFT. And here to the right, I'm showing just the distributions of the various properties that are available for all these 134,000 molecules. So this is a very, very large benchmark set, and it's a lot of groups have published data on it. So there's a lot of things to compare to. And some of the properties that are calculated for these are, for example, Q0, the internal energies, and some free energies, HOMO, LUMO, dipole moment, polaris abilities, and so on. But in the beginning, I'll just focus on the internal energy Q0 here. Okay, so let's look at a real life learning curve here. So a learning curve, on the x-axis, we have the amount of training samples from this QM9 data set. So 100, 1,000, 10,000, 100,000 training molecules. And on the y-axis here, we have the mean absolute error of the atomization energy here in units of electron volts. And this dashed red line here corresponds to the quote unquote chemical chemical accuracy, so 1 kcal per mole. And so here, all these lines basically correspond to one model trained on different training set sizes. And a funny thing is that you can basically read this as a timeline. So the first model here by Matthias Hopp, the Kula matrix from 2012 is the one up here. And then here we have the Kula matrix basically is a matrix that contains the Coulomb interactions between the nuclei in the molecule. And they use that as a descriptor, and it seems to work well. And then in 2015, there is a new descriptor here, the bag of bonds, and then 15, I think this is the BAML, and then 2016, there are some more, and then 17 and 18, basically all these models, which are basically of identical or indistinguishable accuracy here. So the model I introduced before, FCHL, is this black line, which is currently one of the best performers for this data set, at least for this specific property. So you might ask, why is this working well, and why is, for example, these not working so well? So one thing that I've been looking at to kind of visualize this is something we call kernel principal component analysis. And basically what you do is you take some molecules and you calculate a kernel, so the pairwise kernel matrix for example, in this case, I did it for 1,000 of these small organic molecules. And to the left here, we see for the Coulomb matrix, we see the two principal components for this representation and the resulting kernel. And the kernel only knows about the similarity between all the molecules. It doesn't know, for example, about the atomization energy. So in addition to plotting where the molecules are, I also color them by the atomization energy. But it's important to know that the machine does not know these beforehand. And you can see there's some kind of trend here. So these have a very high atomization energy, or low in absolute terms, and then it gets lower and lower and lower as you move up here. And basically the machine will predominantly use these kernel components to interpolate between. And you can see that there's actually some trend, and it looks okay. But there's also, like, the colors are overlapping a lot here, and this makes it harder for the machine to learn or interpolate between these points properly. Now the next representation I will show you is this bag of bonds here, which works a little better. And you can see I tried to annotate with what the molecules are, and you can see it actually divides. For example, up here we have carbon, oxygen, hydrogen in all the molecules in this island. Then we have, I think, also carbon, oxygen here, and carbon, nitrogen, oxygen here, and carbon and nitrogen down here. And you can see the colors are actually spread out a little better here. And then if you go to one of the top performer on this data set, the FCHL model, even though I'm just going to zoom in here. So even though the machine does not know anything about the atomization energy, you can see there's a nice color gradient here, a lot from left to right. And that means that actually it's probably much easier for this particular kernel to interpolate the atomization energies for this data set. And one other thing that is really interesting from this plot, I think, is that you can see there are these vertical stripes here. And actually the vertical stripes, so I tried to, again, annotate what kind of molecule belongs to each cluster. And you can actually see that here we have 20 molecules, or sorry, 20 atoms in each of these stripes, and then 19, 18, 17, and so on. So actually the first principal component of this kernel is actually just essentially a descriptor of the number of atoms in each molecule, which makes sense that that's something that would give you a good atomization energy prediction. And then the second kernel principal component is actually, you can see, in addition to just the number of atoms, it divides it into stoichiometry. So if you go down here, you have carbon and oxygen, and up here you have carbon and nitrogen, and in the middle you have molecules with carbon, nitrogen, and oxygen. And these seem like really nice descriptors basically for the atomization energies, and this is sort of the reason why the kernel from FCHL works nicely for atomization energies. Okay, so of course, I promised that this talk would be about other properties, and I'm going to take a step back to some so a bit of research that came out of my group before I joined the group. So it was done in 2016 and published in 2017, and it was collaboration we had with Google Brain. And of course, Google Brain has a lot of computational power at hand. And the question that they kind of wanted to answer back in 2016 was basically all these new representations were coming out and all these regressors were available. So basically, could they throw a lot of computational power at that problem and then see exactly, for example, if for a given property, what representation and regressor would work best for it in that particular case. And they did that for this very extensive QM9 dataset. And yeah, in addition to that, they also did it for all the various properties. So for example, the atomization in your Homo Lumo and so on. So I'm gonna zoom in on two cases that I found to be really, really interesting. And the two learning curves I'm gonna show here is U0, so the atomization energy, and also the dipole moment here. So this green model called HDAT is kind of a predecessor of FCHL. So let's just imagine that that is FCHL for a moment. And you can see, like, among all these models, actually this HDAT model, it's actually the best, and it's the only one that like really goes below this line here, which denotes chemical accuracy. But then if you go to dipole moments, and this error is in dipole, you can see even when you train on 100,000 samples, it barely even goes below 0.4 dipole error. And that's completely unusable for most works, I think. So when we published the FCHL model 2 years ago, actually the learning curve for FCHL, it would be like, it's completely off the chart here because it's so much better than things were in 2017. So I thought, okay, our model crushes atomization energy, so it probably also crushes the dipole moments. But to my horror, I actually discovered that we were actually one of the worst models for dipole moments. And the funny thing is, this graph here, or this curve here, is from a molecular graph neural network, and it actually reaches chemical accuracy at a little over 100,000 training samples. But the funny thing is that this particular combination of regressor and representation is actually so bad that it's not even on this chart. So basically what we found was that there is no single model that is good for both properties, or like there's no single model that is good for any property in general. Yeah, so that was really hard to understand for us at first. So we started at looking at these kernel PCAs again. So again, I have this kernel PCA. So this is for the QM9 dataset, so just 1,000 molecules for the QM9 dataset, and of course, you get the same. It looks the same as it did before. You have this nice color gradient for FCHL with the atomization energy here on top. And of course, you would expect that if I put a new point in, you could pretty accurately guess what the atomization energy would be just based on these two kernel components. Now, of course, if you color it by the dipole normal from molecule, there's nothing to say that what the kernel sees as the first and the second principal components would be a good descriptor. For example, here you would see that the energy increases as you go from right to left, or it gets more negative as you go from right to left. But there's nothing that exactly says that just because a molecule is bigger or smaller, it should have a larger or smaller dipole moment. So for dipole moments, you have all these physical things and covariances. For example, if you have symmetry in a molecule, the dipole moment can be 0, for example. And then if you just replace one little small group, it can, for example, go from 0 to a very large dipole moment suddenly. So it seems like if we do the regression this way, there's a lot of physics that we don't really handle in the model. And that seems like that's what we're missing for this. So basically, we started to think about, can we do this using response operators? So the operators associated with the response properties. And just to refresh one of the simplest response properties. So for example, the force in a given direction, you can write that as minus the derivative with that coordinate of the energy. And this will give you the force, for for example, force x component, you take the derivative with x. And the same way you can find the electrical dipole moment, you just take the derivative with respect to the electrical field of the energy. Yeah. So let me present how we put that in a kernel, sort of kernel-based regression model. So basically, we have this equation from kernel-rich regression, basically that the energy can be described as the kernel multiplied by the regression coefficients. Now, we also know that any response property, we call that omega here, by definition is given as the response operator applied to the internal energy, or the energy here. So from this here, it follows that we basically take the operator on the left side here. So we could also apply the same operator on the right side here. And what you get is the operator applied to the kernel. And because all these operators are derivative operators, then basically it's a linear operator and you can move the regression coefficients outside here. So basically we end up with this little cute expression here. And so in our paper, we show that there's an analytical solution to this. So you can write down a cost function, and in the paper we show one particular solution to it that looks like the normal equation. Yeah, it looks a bit nasty, but we made care that you could actually train on several different response properties. So omega here denotes the type of perturbation, so the type of operator here. So you could, for instance, train on energies simultaneously with forces, and even energies, forces, dipole moments, whatever, any property, basically, here. Okay, so let me just summarize how this differs from the first type of machine learning we did. So in the conventional kernel-based regression for a given property, for example, U, we would calculate the kernel matrix and we would solve and get a set of coefficients alpha that would correspond to the internal energy. And similarly for another response property omega here, we would calculate the kernel and then we would solve and get a different set of alpha coefficients here that correspond to that particular problem. So essentially the same kernel matrix, and you have a different set of regression coefficients for each property, and you basically have to train a new model for every property, and there is no connection per se between each model here. So now when there's a response operator kernel-based regression, we have the same sort of basic property here. So we have the energy, and you have the kernel, and you multiply that by the alphas. But then if you calculate some response property, you do it by applying the operator to the kernel, multiplying by the alpha. So basically you have the same kernel matrix, but different operators applied to that. And you can train your model such that the same regression coefficients will give you good results in both cases. And so it's basically the same model for multiple response properties. It's how we're doing things. Okay, so let me give an example of how this works in practice. So I'm looking at the electric field first, or properties, response properties. So that's basically the dipole moment here. And so we're training on the energy, and we're training on the dipole moment. So essentially we apply the dipole moment operator to the kernel here. So now this requires you to take the derivative of the kernel with respect to the electrical field. And of course, if there is no response to the perturbing field, you'll just get a zero property. So we have to build some kind of dependence on the external field into our representation. So if you remember, we had this FCHL representation, which was this collection of 1-body, 2-body, and 3-body term. So the way we modified it to have a response to the kernel is we took the molecule and then we placed fictitious partial charges on the atomic center. So for practical reasons, we chose to take the partial charges from the MMFF94 dataset in this case. And then we weight the various terms by the resulting dipole moment. So for example, for the 2-body terms, if you remember from the introduction, we had this 1/r to the 4th scaling term that would attribute more weight to pairs of atoms that were closer to each other. That was this psi2. So to that, we add basically here, I have the expression, so this mu ij. So imagine if you have two atoms, I and j, and you place a partial charge in each, there will be some kind of resulting dipole between those two. And that resulting dipole will have some kind of interaction with the external electric field. And then we have some kind of, I guess we can call it an empirical weight, which we add to this Xi2, which was the 1 over r, the 1 over r to the 4th scaling factor here. And the same thing for 3 body terms. So if you have 3 atoms and they all have a partial charge, they will have a resulting dipole moment and they will have some kind of interaction, and we add that to the scaling function. So let me just show you how this radically changes things here. So I have a toy system here, and it's a hydrogen fluorine molecule, so one of the simplest molecules there is with a dipole moment. And I put that in vacuum with an electric field, and then I change the angle of the electric field with respect to the angle of the molecule here. And you can see the red curve here is the energy you get if you calculate this at the MP2 level. And so for training my model, I choose only one point here, and this is a red point here. So if I start by training on only the energy, the model will not know anything about dipole moments or electric fields or anything, and you'll just get, if you try to predict the energy at any of these rotations, you just get this flat line, so it's very boring. Now, if you instead add also, instead of just training on the energy, you also add the dipole moment of the molecule to your training, you actually get astonishingly good learning. So if you can maybe see next to this red line, there's this blue dashed dotted line, which basically follows it almost exactly here. And this is what you get just by training on this one point and its dipole moment and energy. And this is because all the rotational properties of the physics are encoded sort of in this in the operator, basically. So you can see this, instead of having to train on points all the way along this axis, we actually just naturally get, we learn the entire curve just from one point. So we hope that this would be the way to go forward with these operators. So let's see if they actually help us learning the dipole moment of this QM9 dataset. And it turns out they actually help a lot. So the red curve here corresponds to just learning the dipole norm with normal rich regression or kernel rich regression. And the blue curve here is the learning curve you get if you train on actually the components of the dipole moment here. So it turns out that you actually need whooping 20 times less data. So instead of using 10,000 data to reach this accuracy, you only need 500. So this is much more efficient with your data to do it this way, even though it's the exact same representations and it's the exact same data that you're training on. It's just a much, much better way to do the regression. Okay, so other response properties that people are interested in are those that will give you the potential energy surface here. So again, I have my favorite molecule, hydrogen fluorine, and I used a quantum method, a semi-empirical quantum method called OM2 here, and I calculated the energy here. So basically, the energy you get if you stretch or compress this molecule. And it looks just like the Lennard-Jones potential or something. And then I add these 4 red dots to my training set. So, and at first I will just train on the energy using the normal kernel, and I will learn the regression coefficient, and I will predict all the other points. So let's see how that looks. And this is using our finest FCHL model, and you can see it looks kind of crappy, but the computer does exactly what I asked it to. So basically, learn this model is to ask it to make a model for me that goes through all the red points exactly. But unfortunately, you get this weird transition state close to what would normally be the equilibrium length. So this is very, very crappy, and you would probably need much more data points to get a better model for this. So now let's see what happens when we, in addition to the energy, we also train on the forces. So basically, I tell my computer, make a model that goes through not only the red dots here, but also has the same gradient at those points. And as you can see, basically, we get a model that not completely is correct, but it's definitely vast improvement over the previous model, right? So hopefully we think that this will be a much better way to learn potential energy surface. So let me just show you how including energies and forces in the training, how that alters your learning. So this is something we're planning to have on Archive this week. So I'm confident I can show you this right now and not get scooped anyway. So basically we train on the energies only, or we train on the energies and forces only. And my data set contains a bunch of small molecules. So I'm showing some of them here. So basically small molecules with up to, I think, 7 the heavier atoms. And for those those are in non-equilibrium conformations, and I have DFT forces and energy for these. And also my data set is constructed such that I only have the same molecule once in the entire data set. So you will never find the same molecule in both the test and the training set, or more than once in the test, or more than once in the training set. So I trained 2 models, the green one with energies only, and the blue one with forces in addition to energies. And actually, when you see, so here, these are learning curves again. So here we have the number of molecules. And in the top panel, we have the atomization energy, so the energy prediction. And the bottom panel here is force component error here. And as you can see, actually, you don't get better energy predictions by adding forces to your data set. However, if you try to predict forces, you actually get a tremendous increase in your accuracy by adding these forces to your training set. And this is because the energies, they live on different potential energy surfaces, but only the energy can tell you the separation between these. However, the forces can tell you something about the shapes of all of these. So this is it was a bit counterintuitive to me at first, that actually forces don't increase your energy learning when you're trying to learn the energies of new molecules. But then you might say, okay, forces give you increased learning, but they also come with, like, instead of have 1 energy per molecule, you have maybe 3. Then you'll have 3 and more training points. So in the right 2 panels here, I have the same learning curves here, but instead of the number of molecules on the x-axis, I have the number of labels. And the number of labels is essentially the numbers of forces and energies for that particular training combined. So here we learn the energies, and of course, when you add the forces, you have many more. You have 3 and more labels, and of course, since it was already worse, it gets even worse here. And for the number of labels here for force prediction, it actually shows that 1 energy will actually give you as much information as 1 force label, roughly. So this is they were, to me at least, very surprising results. And so in our paper that we hope to have an archive really soon, we try to use these observations to come up with good guidelines for generating, for example, new data set, and what you should be looking out for, and what you should add to your data set, and when it pays off to add forces to your data sets or not. Yeah. So yeah, another thing, so here I showed you how to learn, or that our model can learn energies throughout chemical space, but some people are also interested in learning energies for just a single molecule. So one of the data sets that people are publishing on results on is the MD17 data set. So it's basically a bunch of molecules, single molecules, and for that there was an MD trajectory and DFT forces and energies, and we can again make these learning curves for each molecule of the ME energy and ME force component here. And we recently updated our FCHL. So the one I showed you in the beginning we called it FCHL 18 now, and we also have a newer version called FCHL 19, which is a discretized version, which makes everything much faster. And as you can see, so FCHL 19 is the blue and the purple curve here. So these use 2 different regressors, but these are pretty consistently one of the top performing models for forces and energies for these molecules. So one thing I often get questions about is how long time does it take to make these predictions. And I just went for this MD17 dataset just to give you an idea of how long it takes to make, in this case, 1,000 predictions, so it's 1,000 samples. So we have the various molecules here from the MD17 dataset and the timing on this axis. And we have these three different models, which basically are different regressors or different, the analytical or the FCHL 19, the discretized version. And basically for the fastest version, which is also one of the best performing versions, we have this, we can predict forces and energies in about, it depends a little bit on how big your training set size is and how big the molecule and such. But if we're in the order of milliseconds for some training sets, that would be way larger than it actually would have to be. So you can definitely run MD simulations with our code today, is what I'm trying to say here. Okay, so the last science thing I will show you before I round this talk off is just something to give you a flavor of how basically how flexible this framework is. So up until now, I've only shown you first derivatives, so forces and dipole moments. But of course, you can also mix derivatives and you can make second order derivatives and so on. And one of these things that if you want to convince somebody that you have a really good potential energy surface for a molecule, that's the infrared spectrum. So what we did to see if we could produce infrared spectra with our code is we basically hooked it up to Gaussian 09, which is capable of doing vibrational analysis. And then for a molecule, we choose this dichloromethane. We made a training set that consists of distorted geometries for this molecule, and then we calculated the energy, dipole moments, and forces for this molecule. And then we basically put everything into Gaussian, and it tells it to basically make us an infrared spectrum. And again, I'm trying to show some kind of learning curve just to prove that our method converges to the sort of the ground truth eventually. So down here we have 5 training samples, so just 5 distorted geometries in the training set. And you can see, of course, you get a very crappy spectrum. And as you increase to 10, 25, 50, 100, you can see the peaks very quickly. They get the right location, and eventually they also get sort of the right intensity from this. So we definitely have a code that can, they can produce the right result given the right training data, even for some more complicated response operators here. Okay, so I think this will be the last thing I will say today. So everything I've talked about, we've implemented this code called the QML code, which is Python 3 toolkit, and it's completely open source with an MIT license. And we have a manual with examples, and you can install it via pip. And we have a website, and this is our GitHub if you want to check out the code for yourself or contribute or whatever. And also, this is where sometimes tweet about chemistry. So yeah. I think that was it. Thank you.
Okay, thanks a million. So as a visual thing, so there is no live clapping, but I think I'll thank you and congratulate on behalf of everybody watching. So I guess we're now opening for questions, and there's already a couple of questions I see in the chat box, and I also invite people to keep adding to those questions. So the first question is from Matthias Rapp, which I guess you know, and he's asking, when you calculate the learning curve offset and slope, do you weight the training set size? And essentially the question is, in particular for small sizes model, the performance can deviate significantly from the asymptotic behavior.
Right. Hey, Matthias, and thank you for your question. So I think the best thing, so let's go back to the learning curve here. So I found the best thing to enforce this linear behavior, especially I think I have a better example actually. Here, so to enforce this linear behavior at the very small training set sizes, I think the best remedy is actually just to do more folds. So I've done up to, in some other cases, in this paper, I've done up to 100-fold random subsampling cross-validation, and eventually that'll give you almost completely straight lines as long as you keep adding enough folds to get a proper mean. Yeah, the mean of the mean absolute error, for example. Yeah.
Okay. Now, the other question I have is from Rajashri Tiwari, is in my own group, and essentially is asking something about the QM9 data set when you show all the, I guess when you show all the different learning curve for different representation.
So is it this?
No, I think actually I'm not 100% sure, but no, I think it was before. Yeah, I think probably this one here. And he was essentially asking that so that the y-axis doesn't seem either uniform or logarithmic. So whether you can explain how you represent
okay. it. Yeah. So it is actually logarithmic, but I guess
okay,
maybe the ticks and the labels are just poorly chosen. So
okay,
it does look a bit weird. I agree to that.
all right, okay. Okay, I don't have any more questions on the mailing list. I have a couple of questions myself. Now, I just wonder. So can you go through again the explanation of how you introduce the derivative with respect to the field when you discuss the dipole moment?
Yeah. Okay. So let me go back to where I introduced the FCHL representation here. So here, imagine we have these Gaussians, for example. Let's just look at the two-body part here. So we have these Gaussians that basically are placed at the distance of, for example, these two carbons. And those are scaled by this 1/r⁴ term here. So in the end, when we calculate this integral, this to the left will be like taller, and this to which one is to the right, because it's further away, it will be smaller. And this is to add more weight to this, which is closer. Now let me find the electrical field here. So this psi2 is a 1/r⁴. So what we do for example, this pair of two, so I guess it'll be an oxygen and a carbon. So you place a charge on each of the two atoms, and those charges will give a dipole moment, and that dipole moment will have some kind of interaction with the external field. So basically, you want to put in the external field into your representation because that's what you want to take the derivative with respect to. And you take this and you add it to this weight factor, and basically now you've constructed a representation that contains the electrical field. So I think one thing that is worth keeping in mind, so we use these partial charges. That doesn't mean that the dipole moment of, for example, this molecule here will be the dipole moment that you get from MMFF94. So you can imagine if you choose one set of charges, they will give you one set of alpha coefficients to fit the dipole moment to which you fit them. And if you choose another set of partial charges, then you'll just get a different set of regression coefficients. So it sort of becomes independent of your choice of fictitious charges. And it actually, in practice, it also seems very insensitive to the choice of charges, as long as they are kind of physically meaningful. So we even tried, just to see how insensitive it was, we tried to just use +1 or -1 or 0 for the partial charges, and that gives you the exact same performance as taking them from QM or from a force field. So we just chose to do it from a force field just because it's the easiest way to generate charges for a given molecule.
Right. Okay. So I have another couple of questions actually. So one is still on the this FCHL representation, and so I just wonder here. When you start to go to multi-body term, is there a cutoff length somewhere? So you decide what is in your neighborhood, I guess.
Yeah. So let's go. I think this is the previous. Here we go. So we actually don't have. We have in our code we have a distance cutoff, but in practice I just set it to infinite, at least for these molecules. But I want to say if you go, the costly thing is if you go beyond 3 bodies, so if you go to 4 body terms, for example, then it becomes just calculating one kernel element almost becomes more expensive than running a DFT calculation.
Right.
Just because of the combinatorial explosion.
So I mean, so when you're on a free body, I mean, so how long is your vector? Say for
So for this representation, it's actually not a vector. We do everything analytically.
Okay.
In the computer, but we also have a discretized version of these, and for those, it actually depends on how many different element types you have in your vector. But it's like, yeah, maybe 200, 300 or something. The vector.
Okay, and maybe the last question for me actually is when you start to look at I mean higher derivative of your energy, right? So I mean you show the forces, but then actually you can keep going, right? Depending on what you want to calculate. How tough it become?
Yeah, so that's actually a good question. That's something I forgot to mention. So right now maybe I can show you that here. Our model is it's not polarizable. So actually the second order derivative, so you take the derivative with the energy or the electrical field twice, it actually becomes 0. So
okay,
our model is not like, it doesn't describe polarizability actually. You would just get 0 in this case. But you could do that if you in some way folded that electrical field into this the way you construct the local dipole moments.
Yeah, I mean, I was just wondering because I mean, you show very convincingly that when you look at energy and forces, one information is, I mean, whether you have in the energy or in the forces is 1-for-1, so that essentially have the same weight. I was wondering actually whether you are going to pick up energy and higher derivative beyond the first derivative, whether you still have this sort of equal weight between your data.
Yeah. So the principle will work basically to any order, as long as that derivative gives a physically meaningful response. As long as your representation has a physically meaningful response to that operator. So essentially, I think we can go to any order with the coordinates, but only to first order right now with the field, the electrical field.
Yeah. Okay. Okay. So there's another question still from Matthias, and he's asking. So he's asking actually whether you can use a discretized version of the FCHL as a feature vector, or is it tied to the kernel that you compute?
Yeah, so that's a really good question. Actually, you can. It just works like any other representation. So you can use it as features for everything, and our code just spits out NumPy arrays. So I hope it's portable enough for most people's use.
Okay. Okay. So I don't see any further question here on the list. So unless there is something very urgent coming, I guess probably we can close here. So yeah, so let me thank you again for the talk, and thanks everybody out there for watching. And the only thing I have to say that we're going to have another talk next week, and Artem Organov is going to give a talk, and then we probably stop for kind of a short summer break. Okay, thanks a lot again, and I think we can close the stream.